All right, let's talk Gaussian elimination. So our problem we're solving today is solve the following system of equations by Gaussian elimination. Here's our system of equations that we're going to do. Okay, first of all, what is Gaussian elimination? Why is it useful? Essentially, Gaussian elimination is a way of taking a system of equations, like these polynomials we have up here, and turning them into like a matrix and allowing us to do linear algebra on it. Computers really are good at linear algebra, so essentially it makes it so that we can linear algebraify this system of linear equations. All right? So what we do is we make an augmented coefficient matrix, which sounds all fancy, but essentially what we do is we're going to take the coefficients from all these x variables, x1, x2, and x3, put them into a matrix, and augment it with the answers on this side, do some row operations in order to get it into an upper triangular matrix. An upper triangular matrix is one that looks like this. It's upper triangular, which means we have numbers up here, and we have zeros down here, okay? Upper triangular. We want to get it into that form. Why do we want to get it in that form? Well, if we have it in that form, let's take this last row, for example. If x1 equals 0 and x2 equals 0, then this and this are just nothing. Then we just have the answer, x3 equals 5. We can take that one, plug it into the one above, and just keep on chugging along and solving. So that's why we want to get it into an upper triangular form. So let's do the first part. Let's represent it into an augmented coefficient matrix. All right, we'll do the coefficient side first. We're going to put all of our x1s here, our coefficients for the x2s here, our coefficients for the x3s here, and then we'll do the augmented side after. Okay, let's start at the bottom. x1, there's an invisible 1 times x1, so we get a 1 here. x2, we have negative 3. x3, we have a 1. Okay, we just took the coefficients, whatever these things are being multiplied by, our x's, and we put them there. Now let's take the second row. x1 times negative 4. x2 is being multiplied by 2. x3 is being multiplied by negative 3. Those are our coefficients there. And now our top row. So this is what can be kind of confusing, especially when you have a longer system of equations. Some people will make the mistake of putting an x1, a negative 1 here, and a 2 here, and a 0 here, because that's what it looks like positionally. That is incorrect, okay? You can see why. Our x2 should be right there. So the negative 1, our coefficient for the x2 should be right here, but instead we put the coefficient for the x1 right there. That's not what we want. Okay, so a helpful thing that a lot of people will do is they'll just rewrite the first row. So 2x1 minus x2 plus 0 x3. That's what they'll do, just so they can keep in mind where the 0 is. The 0 is being multiplied by the x3. The 0 is the coefficient for the x3. So let's put that there. x2 is negative 1. x1 is 2. Now, we're going to augment the matrix. The reason augmenting the matrix is just drawing a line here. You can leave out the line. I like the line because it helps me remember this line is like an equal sign. The reason that we augment the matrix is because whatever row operations, like in algebra 2, you can add one system of equations to another to simplify it. That's essentially what row operations are. When we do that, we have to add the other side of the equation as well. So we can't forget what this is equal to. If we add, the first equation to the third equation, we have to add the other side of the equation to the other side of the equation as well to keep things equivalent. Okay, that's why we have an augmented matrix. Now, Gaussian elimination, there's a lot of different ways you could probably do it, but the fastest way to do it, because mathematicians have figured this out, the fastest way to do it is to start under your first pivot. So start under this top corner and go down. They call this a pivot. So a pivot is just something that's going to have zeros under it. So first pivot, we're going to turn this into a 0 first. Then we're going to go underneath it. We're going to turn this into a 0 second. Now we're going to take our second pivot, which is going to be this guy. Because remember, we're making this upper triangular. We're making a little triangle here. So then we're going to eliminate the third one. Okay, that's the order. 1, 2, 3. So let's start. So what can we do? We have to multiply the first row by something to eliminate the 4 in the second row. So if you're not sure how to do that, like a lot of times people can do this in their head and be like, oh yeah, I know what it is. But if you don't know, think about it like this. We're going to take some a that we don't know, times that by 2 from the first row. That's going to be minus 4 equals 0. Essentially, we want the second row to equal 0. So what do we have to multiply the first row by, this 2 by, to get it so that this equals 0? So that's one way of setting it up if you can't do it in your head. Which with fractions and stuff like that, sometimes it can get really tricky. So it's add 4 to both sides. That's going to eliminate, that's going to get rid of that. And then we're going to divide both sides by 2. So a equals 2. So that is what we need to use. So we're going to do, this is our row 1, this is our row 2, this is our row 3. We're going to do 2 times row 1 plus row 2 for our linear combination. All right. That's what this a was. We're using that here. Okay, so what I like to do is just write all the ones that we're not going to use. Well, the ones that aren't changing, we're not changing row 1 or row 3. So we can just leave them the same. Now we're going to multiply row 1 by 2 and add that to row 2. So 2 times 2, the row 2, the first element here, row 1. 2 times row 1 plus row 2. So 2 times 2 is 4, minus 4 is 0. That's what we wanted, so glad we got that. Now we have to do it with the rest of the row as well, and the other augmented side. So 2 times negative 1 is negative 2, plus 2 is 0. 2 times negative 1, 2, plus 2 is 0. Yep, we just killed our pivot there. Okay, 2 times 0 plus negative 3. 2 times 1 is 2 minus negative 8 is negative 6. Okay, so we ran into a bit of a hiccup. We lost our second pivot. This guy is pretty useful for when we need to get rid of this element here. Now we don't have it anymore. So what can we do? This actually is a blessing in disguise. So what we can do is we can switch these rows around. And some people would be like, wait, are we allowed to do that? Yeah, these systems of linear equations, we just arbitrarily put them in this order. Certainly we can switch them around and it doesn't do anything to the entire system of equations. So let's just do that. So the way of representing this interchange, row interchange, is we do row 2, swap with row 3. All right, let's write the rows that don't change, which is just row 1. Now we're going to write row 3 here. I don't like this 5. I don't like this whole bottom of the matrix. Let's make it a little bigger. And now we're going to put row 2 here, which is 0, 0, negative 3, negative 6. The reason this is a blessing in disguise is because we wanted these two elements on the bottom row to be 0 anyway, right? Now all we need to do is to get this one to get it to have that upper triangular form. Don't forget the triangle. So we just need to turn this into a 0, and then we're done. We're done with Gaussian elimination. So let's do that. Again, same process. So a times 2 plus 1, right? We're getting the 2 from here, we're getting the 1 from here, equals 0. So how can we turn this 1 into a 0? What can we multiply 2 by to get this 1 to be a 0? Let's just walk it through. So do a little bit of algebra. Divide both sides by 2. So we get a equals negative 1/2. So that's what we're going to do here. negative 1/2 R1 plus R2. Oh no, we're rotating. Okay. Write the rows that don't change. 2, negative 1, 0. 1. We're doing 0, 0, negative 3, negative 6. And now let's do negative 1/2 times row 2 plus row 1 plus row 2. So if you can't do it in your head, you can write it out as well. I would suggest doing it in your head because it can get really messy when you're writing down everything. But let's just write it down for those that maybe have an issue with that. So we have row 1 right here, which is, okay, so we have negative 1/2, first element of row 1, which is a 2, plus the first element of row 2, 1, equals 1. So negative 1/2 times 2 is just going to be negative 2 over 2, which is equal to negative 1 plus 1 is 0. That's what we wanted, so we're good. We got a 0 there. All right, erase. Do the next one. Negative 1/2 times negative 1 minus 3, because we're taking the second element of the second row. Negative 1/2 times negative 1 is just 1/2 minus 3. So 3 is the same thing as 6/2. Subtract that through, and that equals negative 5/2. So I'm going to write negative 5/2. I like to write the fractions in a little bit more diagonal way because they fit better into the matrix. So when I put them in the matrix, that's how I put fractions. Okay, rotating again. Let's take the last one. We have 0, negative 1/2 times 0, plus R2, which is just 1. 0 times negative 1/2 is just 0, plus 1 equals 1. Now, we can't forget, we also have to do the other side of the equation. So, we have negative 1/2 times 1 plus 5 equals what? Negative 1/2 times 1 is negative 1/2. 5 is actually 10/2. So then we get 9/2. Okay. Now our matrix is in upper triangular form. Da, 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 da. We have all zeros down here. This is not a triangle. Okay, but now that it's in upper triangular form, now we can do back substitution. Remember what these were? This is x1, this is x2, and this is x3. So back substitution is essentially we plug these in and we get the same equation out. Okay? So another way of writing this is you can write it ax equals b, where this is b here, our matrix here, 1, 9/2, negative 6. Our variable matrix, x1, x2, x3, and then our coefficient matrix is the A. This is a way that it's commonly written. Negative 5/2, 1, 0, 3. The reason it's written this way is matrix multiplication. If we multiply this through, essentially you get these x's put in the right places for all of these. So that's another way that you can write it. So let's convert this back. So 2x1 minus x2, 0x3, which is nothing, equals 1. And then we have 0x1, negative 5/2, x2, plus x3 equals 9/2. And on the bottom one, we have negative 3, x3 equals negative 6. All right, now we're going to do some back substitution. But first, let's solve for x3. Negative 3. Divide both sides by negative 3. Cancels that. That means x3 equals 2. Now we're going to take x3 This is our solution there. We're going to plug that back into there and solve for x2. This is why we did Gaussian elimination, so that we can have one variable by itself on each row. And you might be thinking, this is just so much harder, but honestly, the reason it's harder is because you're not a computer. Okay? Representing these things, these system of equations, into a computer is a lot easier when you put it into a matrix. The computer can understand that. The computer can jump right through. It's a way of systematizing and making an algorithm that will go through and do this process. All right, now let's solve for x2. Minus 2 on both sides to get rid of that. Then we have negative 5 halves x2 equals 9 halves minus 2. Well, minus 2 is the same thing. If we get that in halves, is 4 halves. 9 minus 4 is 5. So 5 halves. Negative 5 halves on this. We can multiply this by negative 2/5. That's reciprocal. That cancels out. To multiply this side by negative 2/5 as well. So that cancels out there. So x2 equals, cancel, I mean negative 1. So x2 is negative 1. Now that we know what those two are, we can plug them in. There's no x3 in the first equation, so all we need is x2. So we have 2x1, plug in x2 next, negative x2, so negative 1, and that's equal to 9 halves. All right, negative times negative 1, this is positive 1. Now we're going to minus 1 on both sides. Okay, that gets rid of that. 2x1 equals 9 halves. All right, let's not write it this way, let's write it the other way. Not the matrix way. Minus 1, which in halves is 2 halves. All right, 9 minus 2, 7. And then we're going to divide both sides by 2. Or times by 1/2, same thing. That's going to get rid of that on that side. So then x1 equals 7/4. Now we found all three. So we can rebuild, we can write our X matrix. So our answer, our X matrix, the thing we were looking for, it's going to have 3 numbers in it, where x1 is 7/4. x2 is, zooming in forever. Actually, let's use that. Let's zoom out so we can see. 7/4 x2 is negative 1, and x3 is 2. I think that's why it's good to label them x1, x2, x3, so you can get them in the right order if you're going to put them back to a variable matrix. Okay, so let's see if that's our answer. It looks like it is not. Where did we make a mistake? x1 equals 0. x1 minus 1/2, minus x2, which x2 we got right, it's negative 1. Oh, it's equal to 1, not equal to 9 halves. That's where we messed up. We got the wrong number here. See, this is why computers do this, is because it's just tricky for us. So let's try this one again. Let's solve for x1 one more time. Hopefully you caught that and we're screaming at me. Negative 1, 2x1 equals 0 divided by 2x1 equals 0. So x1 does not equal 7/4. x1 equals 0. Why are you not letting me erase? It just wants me to live with my mistakes. It wants me to endure. Okay, let's write the X matrix again. 0, -1, 2. And that's our answer. So you have to be really careful about what you're setting things equal to. It's easy to get a little bit lost and confused. My little one there, I got lost there. So that's why computers do it. That's why we don't. So if you have any questions or anything else, comments, suggestions, let me know.